So now that we have seen how arbitrary functions act on sets, let's see what additional behavior occurs when those functions are injective or surjective. So new theorem. Let f be a function from A into B. Let C be a subset of the domain A. Let D be a subset of the codomain B. And let the collection of sets C sub I for I in some indexing set I be an indexed family of subsets of the domain A. Then, if the function f is injective, then the inverse image of the direct image of the set C is the set C. And if the function f is surjective, then the direct image of the inverse image of the set D is the set D. And if the function f is injective, then the direct image of the intersection of the subset C sub I of the domain is the intersection of the direct images of those sets. So proof. First statement, let X be an element in the inverse image of the direct image of the set C. Then Y, which is f of X, is in the direct image of the set C. Now, by definition of the inverse image, X is an element in the domain A, but since Y is in the direct image of the set C, there exists an element C in the set C such that Y is equal to f of C. And so we have that f of X is equal to f of C. Now, since the function f is injective, the element X is equal to the element C. And as the element C is in the set C and the element X is equal to the element C, we have that the element X must be in the set C. That is, if X is in the inverse image of the direct image of the set C, then this implies that X is in the set C, and hence the inverse image of the direct image of the set C is a subset of the set C when the function f is injective. So conversely, let X be in the set C, then f of X is in the direct image of the set C, and so by definition of inverse image, the element X is in the inverse image of the direct image of the set C. That is, if X is in the set C, then this implies that X is in the inverse image of the direct image of the set C. And hence the set C is a subset of the inverse image of the direct image of the set C. And since we have demonstrated set inclusion in both directions, the sets are equal, And so the inverse image of the direct image of the set C is equal to the set C when the function f is injective. So second statement, let y be in the direct image of the inverse image of the set D. Then there exists an element x in the inverse image of the set D such that y is equal to f of x. Now as x is in the inverse image of the set D, f of x is in the set D, and y, which is f of x, is in the set D. That is, if y is in the direct image of the inverse image of the set D, then this implies that y is in the set D, and hence the direct image of the inverse image of the set D is a subset of the set D. So conversely, let y be in the set D. Then for an arbitrary function, since D is a subset of the codomain, it is not necessarily true that elements in the domain A were mapped onto elements in the set D, but since the function f is surjective, the range of the function f is the codomain B, and so the set D is a subset of the range of the function f, and thus there does exist an element x in the domain A such that y is equal to f of x. So as f of x is in the set D, the element x is in the inverse image of D. And so by the definition of direct image, we have that f of x, which is y, is in the direct image of the inverse image of the set D. That is, if y is in the set D, then this implies that y is in the direct image of the inverse image of the set D, and hence the set D is a subset of the direct image of the inverse image of the set D when the function f is surjective. And so we have demonstrated set inclusion in both directions. And so the direct image of the inverse image of the set D is the set D when the function f is surjective. So third statement, it remains to show that the intersection of the direct images of the set C sub I is a subset of the direct image of the intersection of the set C sub I, since by a previous theorem, it is always true that the direct image of the intersection of the sets C sub I is a subset of the intersection of the direct images of those sets. So let Y be an element in the intersection of the direct images of the set C sub I. Then Y is in the direct image of the set C sub I for every index I. And so for every pair of indices I and j in the indexing set I, there exists an element x sub I in the set C sub I such that y is equal to f of x sub I, and there exists an element x sub j in the set C sub j such that y is equal to f of x sub j. That is, f of x sub I is equal to f of x sub j for any pair of indices in the indexing set I. Now, since the function f is injective, x sub I is equal to x sub j. In other words, the element x is in the intersection of the set C sub I, and thus y, which is f of x, is in the direct image of the intersection of the set C sub I. That is, if y is in the intersection of the direct images of the sets C sub I, then this implies that y is in the direct image of the intersection of those sets, and hence the intersection of the direct images of the sets C sub I is a subset of the direct image of the intersection of the set C sub I. And so since we have set inclusion in both directions, the sets are equal, and so the direct image of the intersection of the sets C sub I is equal to the intersection of the direct images of those sets when the function f is injective. Okay, so new definition. Let f be a function from a into b, and let g be a function from b into c. Then the function, which we denote g circle f, which is a function from a into c, defined by g circle f of a is g of f of a. This function is called the composition of F and G So let's look at some map diagrams. The function A is mapped into the function B, or the set B rather. The set A is mapped by the function F into B, which is mapped by the function G into the set C. And so we have an element A in the set A being mapped to an element F of A in the set B, which is mapped to G of F of A in the set C. And so the composition of F and G is the function that maps the set A into the set C by way of the set B. So notice that the composition of F and G is a set of ordered pairs A, C, where for every element B in the range of F, we have that F of A is equal to B and G of B is equal to C. So let's prove a theorem. So again, let F be a function from A into B, and let G be a function from B into C. Then, if F and G are surjective, then the composition of F and G is surjective. If the functions F and G are both injective, then the composition is injective. And if the functions F and G are bijective, then the composition is bijective. So proof. First statement. Now, since the function f is surjective, the range of f is the entire codomain B, and we have that for every element B in the codomain B, there exists an element A in the domain A such that B is equal to f of A. And since the function G is surjective, then the range of the function G is the entire codomain C, and we have that for every element C in the set C, there exists an element B in the set B such that C is equal to G of B. And so, taken together, we have that for every element C in the set C, there exists an element A in the set A such that G of F of A is equal to C, or that G of f of A is equal to C, and hence the function, which is the composition of f and g, is surjective. So second statement, suppose that the composition of the functions f and g of the element a sub 1 is equal to the composition of the element a2. Now, since the function g is injective, we have that f of a1 is equal to f of a2. And since the function f is injective, we have that a sub 1 is equal to a sub 2. And so the composition of a sub 1 is equal to the composition of a sub 2, or rather, if the composition of a sub 1 is equal to the composition of a sub 2, then this implies that a sub 1 is equal to a sub 2, and hence the composition is injective. So third statement, suppose that f and g are bijective, then f is both injective and surjective. Similarly, g is both injective and surjective. So, by the first statement in the theorem and the second statement of the theorem, the composition of f and g is both injective and surjective. And hence the composition is bijective.